And so I was actually going to write a time cutoff on each subject, but I'll simply every once in a while look at the list and get nervous and cut off questions, probably. And actually the first two are probably the longest single items. So last time we talked about staying within a given, the n equals 4 theory, say, and just looking at non-conformal vacuum with the Coulomb branch. The next simplest thing would be to perturb the theory a little bit, to add some relevant operators in Hamiltonian density of the CFT, and I'll suppose here this is irrelevant, delta less than D. If it's irrelevant, it does nothing at low energy, it blows up into UV, and you don't really have a theory anymore in general. Actually, the case delta equals D is interesting, but there's only so much time, so I'll just put a few references in the notes. Anyway, where delta less than D, this is something which becomes effectively larger as you flow to lower energies, and so to change the low energy physics. And we know how to study this in the dual theory, in the gravity theory, because this is adding this to the Hamiltonian is just what we've been doing to make a generating functional. And we've been thinking the generating functional as just being a way to generate the correlate of the original theory, but it's equally well a quantum field theory in its own right. So with the sign convention I was using, this is taking that for J of x I was coupling to the operator and just setting it to some finite constant value. I guess it's a sign convention, yeah. So we now have some perturbation of the boundary conditions, and remember, this means turning on a non-zero value for the previously fixed mode. So the bulk field goes as Z to the Z minus delta, which is just right. When delta is less than D, this grows as we move away from the boundary towards lower energy, exactly like, of course, the corresponding operator. And then we have to figure out what happens when the perturbation becomes large, at large Z, low energy, things become nonlinear, and then we have to figure out what happens next. And it's actually, within the n equals 4 theory, there's a nice example, a rich example, that I'll describe, which is to add to the superpotential masses for 1, 2, or 3 of those n equals 1 superfields. So 1, 2, or 3 non-zero. And this is going to have to be fairly descriptive, and this section of the written notes will be heavy on references. This is more a guide to what people have done than all the details. But I'll tell you what, for one non-zero mass, it's believed to flow to a new fixed point. A new strongly interacting fixed point. For two masses, it's believed to flow. For two masses, what's left, the massless part, is just the n equals 2 gauge theory, which is just the subject of Seiberg-Witten. It's believed to flow to an SUN version of Seiberg-Witten, which in particular means that the massless sector is a U1 is non-interacting. That the massless sector is a U1 subgroup of the original non-revealing symmetry, which means it is non-interacting. With three masses, the massless sector, the chiral superfields are all massed out. What's left is the n equals 1 gauge field, and that's believed to be a confining theory, and so with three masses it should confine. That's expectations for various kinds of field theory reasoning, and it's interesting to see the way the geometry reflects all of these. I'm not within that, that's a special point within that space. Oh, sorry, you're right, yes, actually, I forgot it. Let me come back to that. That's a really good point. So let's see the way that the geometry reflects all of these. So now the point of view, I mentioned for a while back what the dictionary was. These operators, they correspond to the free-form fluxes on the 5-sphere, and the 5-sphere has no free cycle, so these are not typological, not monopole, just some kind of dipole free-form fluxes. And the supergravity folks have a trick for studying these called consistent truncation, where they write down an effective 5-dimensional theory with this mode, and then solve it. And it's really magic because there's no symmetry that would prevent this. There are the particular mode here, it's some harmonic on the sphere. It's not lower in energy than the other harmonics by a lot. Symmetry doesn't keep permitting with them, but there's some supergravity magic where they can write down a 5-dimensional Lagrangian, solve it, and then lift it to a 10-dimensional solution, and it can be applied to this case. And so first, for the case of one mass of flavor, when they do it, they get a 5-dimensional potential that looks like something like this, where the n equals 5, so this is the potential for this mode. The n equals 4 theory that we've been dealing with lives up here, which seems kind of unmoving, but as we discussed, this mode has a negative mass squared, but if it's not too negative, then the boundary conditions stabilize the system, a la Brighton-Lohner and Friedman, and it's okay not to assume it. We know we're in this situation because if you go back to the m squared equals delta minus d dictionary, being relevant, that is delta less than d, exactly means being tachyonic in the supergravity, and you kind of guess what happens. There's some solution, where the field rolls. So here's its value at the boundary, here's its value at the horizon, and there's some solution which has, here's z equals 0, here's z equals infinity, there's some transition region as you roll down the potential, and then there's a new ADS solution. So this is a particular, this is exactly what the field theory reasoning leads one to believe, that you flow from one strong coupling theory to a new strong coupling theory. You can match up the details of what you expect. Yes, sir.
Stability is equal to 0. Stability is equal to 0.
This is instability?
Yeah.
The field ground is satisfied here, meaning that there is no instability. Tom talked about this too. There is no instability in time, but there's in some sense, but it's not really instability. But you don't roll down the thing in time because the gradient energy protects you. But you can roll down it when you travel in space in the radial direction. That's what you're doing. Sure.
I didn't quite understand what the
I mean, right. If you see potential like this, you don't expect this to be stable, this solution. That's what I'm saying. And I'm saying that it is stable because, I'm not sure if I can understand the question, but I'm saying it is stable because there's also a gradient. There's also gradient energy that if you look at time evolution, actually, in terms of potential up. In zero gravity theory, you have, this is the potential in the gravity theory. Sorry, this is the potential here, and it's up here. Now, with two masses, you can do the same thing, and there's some other direction in the potential that you're flowing in, and this one's different because you end up flowing sort of out to infinity in field space. The two masses, the same strategy, when you lift it to a 10-dimensional solution, gives you a singular solution. So this is with one mass. It does what you expect. Two masses gives you a singular 10D solution. But it's actually got a bad singularity because then you look at it carefully, you realize that it's just a bunch of D3 brains. And so what the geometry is here is that, well, let me draw ADS space, Poincare ADS space, this way, this is Z equals 0 at the boundary, and the spatial things are changing up, and it never gets to Z equals 0. It kind of, it's a bad way to draw the picture. But the point is that the whole space, I should really draw it, the point is that you never get to Z equals infinity. The geometry smoothly rounds off. This is actually not the ADS, but the contact directions here. And this is Z equals 0, and they smoothly round off at some Z equals Z max. In terms of the metric, you have this ds squared is L squared over G squared, A of mu, dxu, dxu. And again, in the ADS geometry, one has arbitrary low energy excitations by moving the excitation to smaller and smaller z. That reduces its energy in terms of the gauge theory as much as you want. But once you cap off the geometry, you can't do that, and so you have a mass gap. So every time a relevant perturbation to a conformal theory, there's a good chance that all you're going to do is give mass to everything, and on the geometric side, that's reflected by capping off the geometry. Here, though, it works out that you've got this plus you have n minus 1 d3 brains, not n d3 brains, sorry. There's the minus 1 is a distraction. We won't talk about that d3 brains. And so the bulk theory exhibits exactly the massless center that you would expect from the field theory. And the thing about Cyber Witness is the whole moduli space, these D3 brains actually have lots of places they can sit. And it's true that when you bring them together in certain ways, you do get, as Tom reminded me, interacting fixed points. Actually, you would expect then on the gravity side to get some interesting geometry as you reach those points. And I remember thinking of it years ago and never figured, if anybody ever figured that out? Homer problem. Yeah, it's a great question. I mean, so part of the problem is that the supergravity folks first have to tell us what the metric is for arbitrary distributions of D3 grains, because this trick gives you special distributions. If they would tell us what it was for arbitrary distributions, then one could bring it to the argument and find out what is the geometry.
You also had a nice geometry picture of the citrus mark. You have to see something special that happens in unit for large animals. We don't really understand for Joe for large animals.
Okay, right. You said we understand that for small number, where it might not be in the geometric regime. Good. Okay, with three masses, you try again the same trick. That is, you get some potential, you follow it off. The 5-dimensional solution you get lists to a singular 10-dimensional solution. Question?
What is the
perfect notation is just it's a solution generating string that doesn't capture everything. For a while it was a goal to try to find the gravitational description of the general point on the moduli space. But it seems to be beyond the supergravity. You don't have to be there, but actually describing explicitly the back reaction of the D3 grains explicitly. It seems like the only question. The people who've done the most of it are Pulse and Warner, and they pushed on the problem, made some progress, but I don't think they ever gave a general solution.
I think the paper that any solution can do is to
it's not smooth when the fields run off to infinity. It's unique that it's a recipe. They look at the radical equation, and it's a trick. And it's a trick which it certainly is one-to-one in the way it's used now. Yes. When you get three masses, this becomes even starker because, let me see what happens with three masses. With three masses, you can do the same thing. The five-dimensional thing flows off. You get a singular 10-dimensional solution, but it's not any recognizable, sensible grain. No, this is in 2B, so there's no 11D left. Yeah, well, again, the two-mass singularity really is just D3 brains. Let me finish telling you what happens with three masses. So with three masses, if you're Max Strassler, you look at the A series side of the duality for inspiration. If your superpotential is, the W is M alpha, then the bone mass is equal, say, phi alpha squared plus epsilon alpha beta gamma commutator of phi alpha with phi beta phi gamma is called trace. And I'm leaving off the constants. Then the F-term equations tell you that, again, I'm leaving off the constants, M phi alpha is epsilon alpha beta gamma commutator of phi beta with phi gamma, which is to say that you have vacua, but for any, so again, these are n by n matrices, and you have vacua for, so there is one vacuum for each n-dimensional representation of SU2, then it doesn't have to be reducible. So there's a huge number of vacua, including the trivial one, phi equals 0, and phi equals 0 actually is the confining one, and the other ones have various sort of mixed confining Coulomb behavior. But remember that the scalar parts of these superfields arose as the coordinates of the D3 brane, and this is saying that those coordinates are becoming non-commutative, which comes back to the question from the last lecture, because Rob Myers explained that when you put D3 branes in a transverse flux, it becomes energetically favorable for their coordinates to become non-commuting, and they pop out in two directions to become D5s. And so the correct behavior of the supergravity with three masses is that it ends on, it actually ends on a D5, or in fact, sums of many 5 branes. And the fact that there are many ways to calculate the geometry reflects the fact that the theory has many vacua. And so there's a nice match between, you see for the several things, there's a nice match between field theory expectation and what supergravity tells you, but also it takes some trial and error in many cases to figure out where the geometry flows to. It's not always obvious. The perturbation gets big, and it's not obvious what the geometry that does, and in particular it's useful to have insight from the gauge theory as well. By the way, you can once one does this, one can go back and figure out what the consistent truncation was doing, and it was trying its best. It was producing some smeared version of the D5 brane. It was steering this to the 5-dimensional object out into like a 6 or 7-dimensional object, and so it was trying very hard to get the right answer. Okay. Now, the last thing I want to say about, I'm pretty much on schedule. The last thing I want to say about this is, I told you that one of these theories confines, and I want to tell you how to see that. So, one observer I did talk about is to measure the potential between a source, a quark and anti-quark source, fundamental, that maps, so the QQ-bar potential. Fundamental. There are fundamental. You can always get fundamental sources. So here is your boundary, and it corresponds. So the string, if you think about it, in going back to Cust and Wilson, is thought to be and one could say more to justify this, but time is short. The way you calculate potential is to consider a string hanging down from the boundary, and then subject to suitable for normalization, the potential is the tension of that string. The potential is the total energy of that string coming from the tension. Now, the tension, the effective tension, action is the local tension times the translation, the gravitational relationship, the translation from local inertial coordinates to the global coordinates. And so the further it hangs down, the less its energy, the further indeed it hangs. And in fact, in an ADS phase, you get, as you must get, because just by its scale invariance as massing units, as you pull the ends further apart, the string hangs down lower, and so it can reduce its energy and stand in such a way that the potential goes 1 over r, that must by symmetry. The coefficient is interesting, but no time for that. In a confining vacuum, on the other hand, we have encountered this idea that there is some Zmax. And so, let's draw this a bit larger. The string hangs down, but it can only hang down as far as the space lets it, and then you pull the ends further and further apart. And most of the string is just running along the bottom of the space at the largest value of z, the most infrared value of z you can get. And so the effective tau of the string is just zero. It confines. And that's what happens with 3 masses. With 2 masses, the submarines, if you will, are not confining. They're Coulombic, but for a different reason than over here. There is a floor to the space, as I was saying, for n equals 2, for the 2 masses, but there's also the implicit d3 branes. And so now I'm going to draw the same picture. So here's z equals 0, where the string hangs down from. Here's the floor, and now I'm looking from a different perspective so I can see, those d3 branes. So I'm looking now from a perspective that sees the 3 directions more explicitly, and so here's your d3 branes sitting at the bottom of the space, and the strings hang down. But once the string ends on a d3 brane, it doesn't go any source of flux. But the flux is just a elongation of the d3 brane. So you get a Coulomb potential for a different reason than you did. So that's the general thing with d3, particularly when a lower dimensional object dissolves in a higher dimensional, ends on a higher dimensional, it doesn't just end. There's always some arrow where it gets.
まあそうですね、かもしれませんね。はい、なんか預かりづらいからね。ああ、すいませんね。はい。はい。
2番目からの人はしてたっていうのを